Okay, so last time we saw hash functions, and I said that I'm not going to go too deep into hash functions. Instead, we are going to today look at more number theory related to cryptography. Go back to the basics, but not the real basics. Oftentimes during the lectures, I talked about NP completeness and all these things, hard problems. Okay, we want to define what are hard problems and give some examples and look at some actual uh, things that we can play with her we can actually see rather than have to do with more proofs and things. Okay, so for that, let us look at groups. So chapter 8 actually starts off with modular arithmetic, and we have already seen that one. So I'm going to skip that part and go directly to groups. Okay. So so what are groups? So groups are sets with a particular operation with a particular operation which satisfies which um okay with a particular binary operation. Let me be a slightly more. A group is a set. A group is a set G along with along with a binary operation which is generally denoted either star or composition or addition, a lot of things. Right now we'll denote it by composition, for which the following conditions hold, for which the following conditions hold. Okay, first, closure. What does that mean? If you take any element G and H, for every G comma H belonging to G, G composed H or G times H should also belong to G. Okay? Second, existence of an identity. Existence of an identity. There exists an identity element E belonging to G such that for every G in G, E composed G is equal to G composed E is equal to G. Okay? So the action of identity should be the same. It should not change anything. 3. Existence of an inverse. Existence of an inverse. Okay? For all G, for every G belonging to G, there exists an element G inverse belonging to G such that, well, let me call H rather than G inverse. There should be an element H such that GOH is equal to HOG is equal to E. Okay? Call H as G inverse. And the final property is associativity. Associativity, which says for every G1, G2, G3 belonging to G, what should be true is that G1 composed G2 composed G3 should be equal to G1 composed, G2 composed G3. Okay, so the order of bracketing does not matter. Okay, a group is called abelian. Group is called abelian. BELR. If in addition it has one more property, it also said it in addition to the above, it satisfies um 5 commutativity. Okay, which is to say for every G comma H belonging to G, G composed H should be equal to H composed G. Okay. Group G is called finite. Group G is called finite. Finite if the following if the number of elements in G, if the number of elements in the set of G, the set of G is finite. Okay, now this might seem like an artificial construction which might not directly apply to cryptography exactly, but it makes a lot of concepts really easy to understand and a lot of proofs become easy. Now, most of the groups that you will be dealing with will always be finite and abelian. Let me just write down this. The order of a group is the number of elements in it. Okay. Examples. Okay, a lot of examples. Most of the groups that you're going to deal with are going to be finite and abelian, where as in the number of elements is finite, and you have, what do you call, a times b is equal to b times a. Okay, the operation need, sometimes I'll refer to it as multiplication, sometimes addition, but it generally depends on the group. For example, examples of groups are the integers under addition. Well, second, the integers, rationals under multiplication. Rationals minus 0, positive rationals. So positive rationals under multiplication. 3. R under addition. Right? Fourth, R greater than 0 under multiplication. Not actually R greater than 0, R minus 0 under multiplication. Okay, now here's something interesting. In the first one, I wrote q greater than 0 just to give you an idea that, oh, if you look at just all the positive rationals, you have that under multiplication they form a group. Every element has an inverse because 2, for example, 2 times 1 over 2 is 1, right? The multiplicative inverse is 1, right? It is closed under multiplication. 2 times 1 is inside the group. 7 times 2 is inside the group. Everything is inside the group, right? Now, when you take r minus 0, you might be thinking, wait a second, if I have -1 and 1, then -1 plus 1 is 0, and that is not in the group, right? But a group has only one operation, so no concept of multiplication, no concept of addition. Concept of addition. When you're looking at multiplication, there is no idea of addition. When you're looking at addition, there is no idea of multiplication. Okay? There's exactly one group. Okay? 5. 0, 1 to the n under bitwise XOR. Under bitwise XOR. Okay? Where the identity is going to be what? I will leave you to figure out what the identity and inverse is. Find the identity and inverse. Okay? And for example, a harder group that you have seen but didn't realize is 2 by 2 matrices, invertible matrices. 2 by 2 invertible matrices. Okay? Some other examples that you have seen before is ZP star, which is equal to 1 to dot 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 p minus 1 under multiplication and 8 ZP, which is equal to 0 to p minus 1 under addition. Both of these were introduced when we looked at affine ciphers, right? And so these are also groups. Examples that are not groups. Examples of not groups. Not groups. First, Z under multiplication. Right? Of y, 2 has no multiplicative inverse. Multiplicative inverse. Right? So does 0. Both of these elements do not have any multiplicative inverse. So even if you had removed 0, it would not have a multiplicative inverse. Second, R under multiplication. R under multiplication. So this time, for example, 0 has no multiplicative inverse. Has no multiplicative inverse. Okay. 3. Any 2 by 2 matrices. All 2 by 2 matrices over reals, maybe. Reals. Okay. Not every matrix has an inverse. Not every matrix has an inverse. Right? So not every group needs to be not every group needs not every set needs to be a group, even with an operation. Okay. Note matrices are not commutative, are not generally commutative. Generally commutative. So that gives you an example. So the example 6 is a non-abelian group. Is a non-abelian group. There are lots and lots of non-abelian groups, but you're not going to be dealing with it generally. Okay. Now, certain notes. Note. The group addition, group operation generally is written rather than composition. We will generally write it as additive or multiplicative. So first, the group operation with the groups we are dealing with is generally written additively or multiplicatively, depending on context, depending on the group context in context. Okay, i.e. write G plus H or G times H instead of G O H. Okay, now note this. Let me just write it this way. This does not mean that the group operation is going to be addition or multiplication as of integers. Okay, does not mean addition or multiplication. Group operation corresponds to addition or multiplication of integers. Right? For example, I might refer to XOR of two strings by addition of them rather than O plus. I might just write plus. Okay, and that is not exactly addition of integers, right? It's something different, but it's a shorthand. Identity is denoted by 0 or 1 respectively. Okay, we denote G inverse G inverse is denoted minus G or G inverse respectively. and group exponentiation as m times a or a to the m respectively. Okay, so if the operation is plus, I am going to be doing a plus a plus a plus dot 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 a m times and this is a times dot 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 a m times. Okay, now when you're doing computations in groups, okay, let me actually write down some important results. Lemma. Let G be a group. Let G be a group. And A comma B comma C belong to G. If AB is equal to AC, then A is equal to B. Then A is equal to B. Okay. In particular, the inverse is unique. The inverse and identity are unique. Okay. Proof. So for now, in the first part, I'm not going to assume that identity is unique. Okay. So suppose AB is equal to AC. Then let A inverse be the inverse of A, and V inverse of A. Then A inverse times A times B is equal to A inverse times A times C. Okay, it is very important that the order be kept this way. If the group is not abelian, multiplying from the right would not give you the same thing, right? This gives, therefore, it is this way. A inverse times A times B equal to A inverse times A times C. Therefore, 1 times B is equal to 1 times C. Therefore, B is equal to C. Okay? Now, if A times B is equal to B, then A inverse times A times B, I'm sorry, not A inverse times A times B, A times B inverse, well, let me just write it in the next line. Then A times B inverse is equal to B times B inverse. Therefore, A times 1 is equal to 1. Therefore, A is equal to 1. Okay? Therefore, identity is unique. Identity is unique. Okay? Now, in part C, if A times B is equal to if A times B is equal to 1 and 1 is equal to C times A, then B is equal to C. Okay, this is a very, very special case. Generally, you can't prove that B is equal to C, but if they're 1, then you can show. Okay, and that is because A, as in this case, B is equal to B times A times C. Well, B times 1, which is B times A times C, which is equal to B times A times C is equal to 1 times C is equal to C. Okay, therefore inverse is unique. Inverse is unique for every A. For every A. Okay. Note, in general, A times B is not equal to B times is equal to B times C does not, well, is equal to C times A does not mean B is equal to C. B is equal to C. Okay, not generally true. Not generally true unless group is abelian. Okay, so this is abelian is named after Abel. Okay, which is why it's written with a capital A. Okay, so this is not in general true if the group is not abelian. Most of the groups that you're going to deal with are going to be abelian. So you can assume that A times B is equal to C times A implies B is equal to C, and that A times B is equal to B times C. A times B is equal to B times A, but this is not in general true. Okay, so in general, groups are very, very interesting, and by itself they're extremely useful. Now, the reason we are interested in groups in cryptography is for their computation. Okay, so computations in groups. Computations in groups. When working with groups computationally, we need to fix some representation of the group elements. Need to fix some representation of the group elements. Okay, generally, not always, usually, okay, not always, you have a unique representation for each given group element. For a given group element. Okay, the representation must be so that it is possible to efficiently identify group elements. Must be possible to efficiently identify group elements. Okay, and it should also be possible for us to efficiently perform the group operation. Must be possible to efficiently perform the group operation. Okay. In particular, um, for what we are concerned with, a lot of times group exponentiation should be computed efficiently. Group exponentiation can be computed efficiently. Okay. Um, so as we talked before, um, most of the times what you will be dealing with, the group that you will be dealing with, is going to be Zn. Okay, which is 0 to 1 dot 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 n minus 1 under addition modulo n. Right? What are the properties of this group? Inverse is 0. Sorry, inverse identity is 0. T is 0. Inverse of A is minus A mod n, which this square bracket symbol basically says, oh, take the number, put it back between 0 to n minus 1, right? And this is associativity and commutativity are obvious. Associativity, commutativity, tativity are obvious. And the order of the group is n. Right? Now, just keep in mind, I can go on and on and on and on about groups. Group theory is an entire subject of math. In my undergrad, I took 3 courses. Undergrad algebra can have um, group strings and fields as separate subjects of group theory. So it can be basically a 3-semester course on groups. So let us not go too, I'm not going to go too deep into groups. If you're interested, you should definitely take a group theory course. But for now, we are just going to stick to a really low level of groups, okay? So we are just going to deal with finite abelian groups, okay? Commutativity means abelian, order is n, so finite, so this is a finite abelian group. Okay, what if I wanted to do multiplication? What if we want to consider multiplication? Multiplication. Well, we run into our first trouble. Zn is not a group under multiplication. Not a group under multiplication. The most glaring reason being that 0 has no inverse. Has no inverse. But suppose you're like, okay, I can deal with that. I will just remove 0. Even if we exclude 0, even if we exclude 0, there might be might be numbers multiplying to 0. Numbers multiplying to 0. Okay. For example, 2 times 4 is equal to 8, which is congruent to 0 mod 8. Right? So clearly, if I have 2 in my group, I cannot have like my Z8 is not a group, especially even if I remove 0 because 2 is in there. Right? So how do we fix this? Fix this by considering the invertible elements. Consider the invertible elements modulo n, which you have seen before, is i.e. Zn star, which is 0 smaller than x smaller than n, such that GCD of x and n is 1. X, n is equal to 1. We have looked at this group before, and now certain things are true. Closure is true. Okay. If you take two elements and you multiply them, if their GCD was initially 1 with n, multiplying two things which have GCD 1 with n will still keep the GCD 1. The identity of this group is 1. Okay. 1 has always GCD 1 with n, so 1 is going to be in there. Inverse is of A is A inverse mod n. And once again, associativity and commutativity. Associativity. Commutativity. Obvious. So you can in a way understand that these are inherited from the integers. The integers are associative and commutative, and modulo n, these are inherited. Okay. Now we introduce a special symbol, phi of n, the Euler-Toten function. Phi, the Euler-Toten function. Okay. What is the Euler-Toten function? Phi of n is equal to the number of invertible elements modulo n. Number of invertible elements modulo n, which is the same as basically is equal to the cardinality of the set, the order of the set 1 to n minus 1, such that GCD of a comma n is equal to 1. Okay, which is basically the order of Zn star. Okay. Now, special case. If you look back up, if you scroll back, you will see that in the examples I gave, I did give a group where I took Zn star, except I took a very, very special group. I said I am looking at Zp star for prime p, which is 1 to p minus 1, prime p. So I probably forgot to mention these here, but p prime. Okay. Whenever I write a p nowadays in this now, it's going to be a prime. Okay. Okay. Special case. If p is a prime, then 1 to p minus 1 all have GCD 1. So they're all invertible, or all invertible modulo p. In particular, that means phi of n, which is the order of Zp star, is just p minus 1. Okay, so these are the nice groups. If n is equal to p comma q, p times q, for distinct primes p comma q, then the only integers then the invertible elements are the integers from 1 to n minus 1 that are not multiples of p or q, right? So in that case, phi of n, which is equal to order of Zn star, is actually equal to well, let us count the number of elements which are multiples of p and which are multiples of q and subtract them from n. Okay, n minus, well, how many numbers are there which are multiples of q from 1 to n? It's going to be q, 2q, 3q, 4q, all the way up to p times q. So there are p of these minus p, plus how many of them are multiples of p? There's p, 2p, 3p, all the way up to q times p. So there are q of these. But there's one that I've counted twice. I have counted n, which is pq, as both p times q and q times p. So I had to add that one, right? Because I counted it twice. So I add the number 1. And so this is just basically pq minus p plus q minus 1, which is equal to p minus 1 times q minus 1. Okay? In particular, lemma, which I'm not going to prove, lemma phi of n times m is equal to phi of n times phi of m. If n comma m, if GCD of n comma m is equal to 1. Okay, I'm not going to prove this, but this is a very useful theorem. Okay. Now, um, let us get back to group theory. Okay, and let me um, show what was a very remarkable result. Okay, initially it was proved by Fermat, and he wrote it down without a proof. Okay, initially, and one of the proofs that was later published, he did give a proof later on. Initially, he wrote it without a proof. Okay, Fermat was a lawyer by job. Okay, and he just dabbled in mathematics for fun. So Fermat has a lot of theorems. Okay, and this was his little theorem, which says for any a um, if for any a, if p does not divide a, then a to the p minus 1 is congruent to 1 mod p. Okay. We are not going to look at this theorem. We are going to look at a generalization of this theorem, which is called Euler's theorem. Euler's theorem. Okay, which says for any a, such that and any n, sorry, a and any n such that GCD of a comma n is equal to 1, we have a to the phi n is congruent to 1 mod n. Okay, I will rephrase that in terms of group theory, i.e. let G be a finite group, G be a finite group so for group theory, there is a stronger theorem that I'm going to use. Theorem. Let G be a finite group. Let G be a finite group. Finite group with m is equal to order of G. Okay. Then for any element, G belonging to G, G to the m is equal to 1. If I'm looking at G as Zn star, then this corresponds exactly to the Euler's theorem. Okay. Otherwise, this result is true. This is the result. Proof. We are only going to prove it for abelian case. Only proving it for abelian case. Only proving for abelian case. Okay. Fix any G. Okay. Fix G belonging to G, and let G1, G2, Gm be the elements of the group. Be the elements of the group. Okay. So G is clearly one of G1 to Gm. We have no idea which one. It doesn't matter. Claim. Claim. G1 times G2 times all the way up to Gm is equal to G times G1 times G times G2 times dot 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 G times Gm, in which case this will imply that if we can show this in this, if this is true, then product of I is equal to 1 to m, Gi is equal to G to the m times product I is equal to 1 to m Gi. Therefore G to the m is congruent, is equal to 1 in the group, as required, right? Because we have shown that the only element which satisfies the property that if I call this entire thing as A, then G to the m times A is equal to A. Therefore, G to the m has to be equal to 1. So how do I show this? If G times Gi is equal to G times Gj, then Gi is equal to Gj, right? By lemma, by the previous, by the same result, right? If G is not equal to 1. Okay, why am I assuming G not equal to 1? If G is equal to 1, then it's trivial. So if G is equal to 1, result is trivial. So assume G not equal to 1. Okay. We have this. What that means is each of the elements on the right hand side, so let me call this as star. Therefore, each of the elements of star is different, is distinct. Well, there are exactly m elements in the group. There are exactly m distinct elements in the group. So the LHS, the RHS of claim is elements in LHS permuted, right? Since the group is abelian, the order doesn't matter. Since the group is abelian, the order doesn't matter. The order doesn't matter, and hence claim is true. Hence hence claim is true, and hence the result is true. Okay. So for example, in Zn, for all a belonging to Zn, we have 1 times a is congruent to 0 mod a. Okay. In Zn star, for every a belonging to Zn star, we have a to the phi n is congruent to 1 mod n. Okay. A corollary of this result, I'm going to stop at that because yeah, it's nearly an hour. Corollary. Actually, let me just stop here. I will follow. We'll look at more related results and which are important and about computations and other things in the next lecture. Okay.